Hello. Uh, we consider a question from Cambridge Assessment International Education, that is Cambridge International Advanced Subsidiary Level. The paper is paper 2, Pure Mathematics 2, which was taken, whose code is 9709/23, and the paper was taken October-November 2019. The question of interest is question 7, which is a continuation of our consideration of introductory calculus, where we are basically dealing with integration and differentiation. So the question is, the equation of a curve is x squared minus 4xy minus 2y squared is equal to 1. Find an expression for a change in y over change in x, which is dy dx, and show that the gradient of the curve at the point where x is -1 and y is 2 is -5/2. That's 5 marks. Now, Roman 2, show that the curve has no stationary points. That's 3 marks. Roman 3, find the x coordinate of each of the points on the curve at which the tangent is parallel to the y-axis. That's 2 marks. So that's all. Let's consider what the solution is. So this is how we look at the solution. We see that y is equal to x squared minus 4xy minus 2y squared. That's what we are given as the equation of the curve, is equal to 1. Is equal to 1. So we are asked to find an expression for dy dx and show that the gradient of the curve at the point -1, 2 is -5/2, and that is 5 marks. So what we'll need to do, if this is the function of the curve, the equation of the curve, then it means that for us to refer to the gradient, we need to differentiate this particular function. So we are going to have dy dx. And what is y? Y is the whole of this. So that means dy dx of what? D, so we say we can, well, dy, and that is like saying d dx of, in bracket where there's y, now we put this, x squared minus 4xy minus 2y squared, like that, minus 2y squared. Then the next step is having to find the values. And we see that this we can find straight, because d dx of x squared will be 2x. But d dx of minus 4xy will now require product rule. We apply the product rule. And the product rule simply tells us that that's the product rule. It's actually this should be d dx of uv is equal to d dx of uv is equal to that. So we need to bring that in this context. So this is the product rule. We want to see how to apply it to get the derivative of this one here. So we will say let u be minus 4x and v be y. V be y. V should be y. This means that this, if u is that, then it should mean that du dx is equal to minus 4. It's minus 4. It's minus 4. And if that's the case, then our dx of uv will then be, if this is u prime and this one is our u prime, that's our u prime, and this is our v. Our v prime is d dx of y. D dx of y. So I'll bring them here. I'll now bring them here. So where there is u prime, that is minus 4. And then where is v? V is y. Then plus, where is u? U is minus 4x. U is minus 4x. Then v prime is this, which is d dx of y. D dx of y. D dx of y. So in effect, what we have is minus 4y. That should give us minus 4y minus 4x d dx of y. Yeah, which is minus 4y. Then this becomes minus 4x d dx of y. That now becomes this. So we say this is minus 4y minus 4x d dx of y. That's that. Now we are left with this part here, this component. So I will say d dx of minus 2y squared of minus 2y squared. Here now we'll have to apply the chain rule. We'll have to apply the chain rule, which is if you have d dx of y raised to power n, then this is similar to saying n y raised to power n minus 1. That's the chain rule. So we need to apply this in this context and see what we are going to have. D, of course, d, it becomes dy dx. Dy dx here. D dx of this is equals to this dy dx. Dy dx. That's it. Dy dx. So let's put that in this context where now we take our y to be the whole of this function, and the power 2 becomes n. N is now 2. So in that context, we see that what we are going to have is minus 2. That is this n, this n. Then the original one with the power reduced. In bracket 2y, in bracket 2y, dy dx, which is minus 4y dy dx, minus 4y dy dx. So that becomes dx of minus 2y squared is equal to minus 4y dy dx. So if I have all that, then I need to bring them together. The first one was 2x. So I have 2x minus 4y minus 4x dy dx. Then minus this, which will be a plus, because it's minus minus. So that will be, actually it's just, okay, this, let me put this so that I follow what's going on. It's minus, there's a minus here. So that I don't lose track, I need to be observing the signs in each step. And so what that means is what we are going to have is 2x minus this. So what I have, it will be plus. So I have minus in bracket minus 4y no. I need to take care of this, and that's why I didn't want to. So I should just leave them the way they were because I'd taken care of that. So it's minus 4y minus 4x dy dx like that. Then minus this. Now minus this, which will be straight away just minus 4y dy dx. Minus 4y dy dx. So this is that is this, that is that. So that's what I have. And if this is the dy dx of the entire function, then I can equate it to 0. And if I do equate it to 0, then what I will end up with is 2x minus 4y minus 4x dy dx minus 4y dy dx is equal to 0. So I collect the like terms. I want dx. I want an expression for dy dx. So I will then say 4x dy plus 4y dy dx is equal to 2x minus 4y is equal to 2x minus 4y. So I can factorize dy dx. So I now have actually 4. I can factorize dy dx so that I have 4x plus 4y inside is equal to 2x minus 4y. But this This just means that I could factorize 4 so that I have it outside 4 like that. Then I just remain with x plus y inside like that. And if I did that, then I can divide each side by this. So in which case I'll be having dy dx is equal to, that will be half x minus y, half x minus y divided by x plus y. Half x minus y, that is half x minus y divided by x plus y. So that is the expression. This is now the expression for the gradient, because we have now equated it to 0 at that point. So if equated to this to 0, then let's see what we have. So it implies that dy dx is that, and if that is dy dx, then the gradient at the point -1, 2, as asked. I'll need this. Let me just have this. So I'll need to substitute. The point is -1 and 2. We substitute it here. So it means that x, okay, this just means that x is -1 and y is 2. So let's substitute those values here. So for x -1, so that will be -half, minus 2 all over 1, because it's 2 plus minus 1. So this gives me, then you have 2 LCM, and that is 1 minus 1, then minus, so that is 4. This gives me -5/2. So -5/2 is as required, because we were asked to show that find an expression for dy dx, which we found to be this, and show that the gradient of the curve at the point -1 and 2 is this, which we have shown. So that is that for Roman 1. So I move to Roman 2. Show that the curve has no stationary points. Show that the curve has no stationary points. So we know that stationary points are the turning points. Basically, they occur at the turning points. It can be minima or maxima. So stationary points occur where dy dx is equal to 0. So it means that we'll now test what we have here. So first, if the Roman 2 will be dy dx, which is equal to half x minus y over x plus y, should be 0. The gradient is supposed to be 0. This is the expression for the gradient. This is the expression for the gradient as we had. But what we are saying is at stationary point, the gradient should be 0, because at that point we are not expecting any change. There is no rate of change. If it's a curve, it's moved up to the point where if it's making a turn, it first has to flatten, then start decreasing. So for that reason, that point is what we refer to. So we equate it to 0. And if we do this, let's see. If dy dx, the gradient itself is 0. If the gradient itself is 0, then What does it mean? Is it the numerator or the denominator which should be 0? Because if the denominator is 0, then we are going to have a very big value here. This value will not be 0. If we have a small value in the denominator, then this will be big. It means if we have 0 at the denominator, this will be infinity. So if the condition now is that the whole of this is equal to 0, then it's either the numerator or the denominator which should be 0. So that because we already know that the denominator cannot be 0, so it is this that is 0, the numerator. So we say half x minus y is equal to 0, implying that half x is equal to y. Half x is equal to y. And this is x is equal to 2y. X is equal to 2y. So if x is equal to 2y, let's substitute x is equal to 2y in the original function, which is this. The original function, which is this. So I rub that. Yeah, so let me first just take it from here. So I want to put it here. So where there is x, I put 2y. So this will be 4y squared now. So first I say 4y squared minus 4y times 2y. That will be 8y squared. That will be 8y squared. Then minus 2y squared is equal to 1. 4y squared minus 8y squared minus 2y squared is equal to 1. If you work this out, this gives you minus 4 minus 2. So we have minus 6y squared is equal to 1. And we are talking about y squared is equal to 1, negative 1 over 6. So what we say up to that point, we say that there are no stationary points on the curve, since this has no real solutions. This has no real solutions. This one here has no real solutions. So that is why we conclude that this is a stationary point. Then Roman 3. So Roman 3, find the x coordinates of each of the points on the curve at which the tangent is parallel to the y-axis. And here again we note that the tangent is parallel to the y-axis where, look, we are used to having the y, the x. But can we try to figure out what the x, the y will look like? Yeah, because if we do that, then what we will see is that the tangent is parallel to the y-axis where the x, the y is 0. So the x, the y is 0 at the point where the tangent is parallel to the y-axis. Look at this. This is the y-axis, this is the x-axis. Now, the moment we have a curve, and by drawing it's a tangent at a point on the curve, the tangent is parallel to the y-axis. We know that parallel lines have same gradient. And what is the gradient of this? We know that it has a gradient of 0. So, if we are saying this is parallel to this, then what we are implying is that the derivative dy dx for this one is undefined. It's now undefined because it's this. So, because dy dx refers to the change along the y-axis and change divided by change in the x-axis. But you see that there is no change in the x-axis here. There's no change. But of course, this is changing infinitely. So for that reason, that is why we take a case where dx dy is equal to 0. And at that point, the dy dx of this tangent is undefined. So using that fact, we proceed and say, from our expression that we had, this expression, because we already found that dy dx is half x minus y over x plus y. So if that is so from the expression for dy dx, this is undefined when do we have it undefined? Just as I said here, it becomes undefined infinity, or rather to say, when it's the denominator, which is 0. It's now the denominator to be 0. For this, for dy dx to be undefined at this point, it only means that the denominator should be small, because as you decrease the size of the denominator, we are expecting the quotient to be big. So the more you decrease it up to the point it gets to 0, this will be bigger. And that infinity is what we want. So this denominator is what defines that condition. So we say that in this case, it is x plus y, which should be 0, implying that x is equal to minus y. If x is minus y, let's substitute this again. So this is when the denominator is 0. So if x is equal to minus y, let's substitute this again into our initial one so that we see what we get. So for that, I'll still come and grab this as I retain that. So in this, if x now is minus y, so minus y squared is y squared. So I'll be having y squared minus 4 minus y. So it will be plus 4y squared. Then just minus 2y squared is equal to 1. So this is 5y squared minus 2y squared, which is 3. Y squared is equal to 1, implying that y squared is equal to a third. Y squared is equal to a third. And so y will be plus or minus root of a third, root of this, because this is y squared is this, so y squared is this, so y will be this, root of a third. So root of a third, like that. Yeah. And this is like saying plus or minus 1 over root 3, because root 1 is 1. So therefore the x coordinates of the points where the tangent is parallel to the y-axis are negative 1 over root a third or positive 1 over root a third. And now that is the way you are expected to answer that question so that you score your marks fully. So up to there, see you in my next video.